Hi, this is the first video of a playlist about the preparation of carboxylic acids. If you have subscribed to this channel, you can find a PDF version of this video under the Community tab. Carboxylic acids are important target compounds and key intermediates for the synthesis of esters and amides. Because esters can often be saponified in high yield, I've also included in this playlist reactions that yield esters instead of carboxylic acids. This first video is about the preparation of acids by oxidation of alcohols. In parts 2 to 4 we'll have a look at the oxidation of hydrocarbons, aldehydes and ketones. Parts 5 and 6 are about carboxylations and carbonylations, and in the last video I'll show you some strategies for hydrolyzing esters, amides, nitriles and trihalides. First, a few words about the properties of carboxylic acids. Their acidity results from the electron withdrawing effect of the carbonyl group and from resonance stabilization by equal distribution of the negative charge on two oxygen atoms. The acidity of acids is given by their solvent-dependent pKa values. The smaller the pKa, the stronger the acid. The equation defining the pKa is shown here. It follows that the pKa approximately corresponds to the pH at which the concentration of protonated and deprotonated acid are the same. In other words, the pKa is the pH at which a given acid is 50% deprotonated. Typically, carboxylic acids have high melting and boiling points, also because of the hydrogen-bonded dimers sketched here. Their solubility in protic solvents is high, and upon ingestion, carboxylic acids are rapidly excreted renally or metabolized to still more soluble compounds. Thus, most simple carboxylic acids can be ingested safely, even in larger quantities. However, their taste and smell, in particular that of C1 to C10 carboxylic acids, is not very appetizing. Typical carboxylic acids, such as acetic or benzoic acid, have pKa's of 4 to 5. This means that at a pH below 4, most acids are protonated and neutral and can be extracted into organic solvents. If the alkalinity increases beyond pH 6, carboxylic acids will be deprotonated and highly soluble in water but insoluble in most organic solvents. Formic and trifluoroacetic acid are particularly strong acids, with a pKa of 3.8 and minus 0.25. Compared to ethanol, formic or acetic acid, despite their similar molecular weights, boil and melt at a higher temperature. All acids shown here are much more acidic than phenol or ethanol. Most carboxylic acids are stable at room temperature. When acetic acid is pyrolyzed at 700 degrees Celsius, it decomposes into ketene and water, not into methane and carbon dioxide. But if decarboxylation yields a stabilized carbanion, then it will often proceed readily. In the video playlist Carbon Dioxide, there is a video about the decarboxylation of carboxylic acids, with many examples and precise reaction conditions. If the carbon atom carrying the carbonyl group can form a well-stabilized carbocation, then the acid may readily decarbonylate, for instance by treatment with sulfuric acid. The upper two rows on the slide show some acids that decarboxylate easily upon heating. These include 3 keto-carboxylic acids, malonic acids, some benzoic and aryl acetic acids, propiolic acids, trihaloacetic acids, cyanoacetic and nitroacetic acid. Alpha-hydroxy and amino acids, as those of the third row, often decarbonylate under acidic conditions. Acids can also decarboxylate when treated with strong oxidants or upon electrochemical oxidation. As intermediate, a carboxyl radical is formed. These are highly unstable and irreversibly decarboxylate to yield carbon-centered radicals and carbon dioxide. The most important carboxylic acid is acetic acid, with a yearly worldwide production of about 17 million tons. The main synthetic strategies are carbonylation of methanol, oxidation of butane, and oxidation of acetaldehyde. In part 6 of this playlist you can find some other examples of the carbonylation of alcohols. The carbonylation of methanol can be catalyzed by iodide and some transition metals, as sketched here. It proceeds by intermediate formation of methyl iodide, which then alkylates the transition metal. Carbon monoxide insertion and reductive elimination yields an acetic acid derivative, which is finally hydrolyzed to the acid. The main uses of acetic acid include the manufacture of vinyl acetate, cellulose acetate, solvents, and various intermediates. Formic acid is produced on a smaller scale, mainly by carbonylation of various nucleophiles. The resulting intermediates are then hydrolyzed to formic acid. It is mainly used for the production of animal feed, in the leather and textile industry, and as synthetic intermediate and reducing agent. Benzoic and propionic acid can be used as food preservatives to prevent the growth of mold and yeasts. Large amounts of these acids can be consumed safely, for instance 10 grams of sodium benzoate daily. Let's now discuss some specific examples of the oxidation of alcohols. The cleanest strategy is by thermal dehydrogenation. Inexpensive and robust catalysts are intensively being sought after, because alcohols could serve as a storage medium for hydrogen. A number of catalysts can bring about the dehydrogenation of alcohols. With copper chromide, a high reaction temperature may be required, as in this example. Only one of the two hydroxyl groups was oxidized, and a lactone resulted in high yield. Here, a mixture of TEMPO and a copper complex was used to catalyze a similar lactonization as on the previous slide. Again, no stoichiometric oxidant was required, and hydrogen was probably formed as byproduct. The dehydrogenation of alcohols becomes easier upon increasing alkalinity of the reaction mixture. Dry sodium alkoxides are actually powerful reducing agents and may catch fire spontaneously when exposed to oxygen. In this example, phenylethanol was converted into phenylacetic acid with a cobalt catalyst and an excess of potassium hydroxide in toluene. Because the oxidation of alcohols to acids almost always proceeds by intermediate formation of an aldehyde, strongly alkaline conditions can also cause aldol condensation. Still, an acceptable yield of acid was obtained here after acidification and purification. Also, ruthenium complexes can catalyze the potassium hydroxide-mediated dehydrogenation of alcohols, as shown here. In this example, diethanolamine was dehydrogenated once by heating with an excess of sodium hydroxide and a small amount of a ruthenium complex. It is not clear why the oxidation proceeded only once. The oxidation of alcohols to acids always proceeds through the aldehyde oxidation stage. Because aldehydes are usually oxidized by hydride abstraction from an acetal or aminal, the oxidation of alcohols in the presence of amines can yield amides directly. In this example, a mixture of benzyl alcohol and butylamine was dehydrogenated thermally with the aid of potassium terzbutoxide and a ruthenium complex. A low yield of N-butylbenzamide resulted. For synthetic applications, it's irrelevant if hydrogen or water is formed as byproduct. Actually, the formation of hydrogen can be dangerous because of the potential formation of explosive air-hydrogen mixtures. I'll show you now some examples of alcohol dehydrogenations with stoichiometric oxidants, beginning with one of the most convenient oxidants, hydrogen peroxide. In this example, the dehydrogenation was catalyzed by sodium tungstate and a phase transfer catalyst. No additional solvent or strong bases were required. This example is similar to the previous one. The reaction mixture was diluted slightly with terzbutanol, and as byproduct 11% of an aldehyde was obtained. Under these conditions, also benzyl halides were oxidized to benzoic acids. Instead of tungstate, also supported gold can be used for such oxidations, as shown here. Hydroperoxides can sometimes be used as a more lipophilic alternative to hydrogen peroxide. In this example, both a primary and a secondary benzylic alcohol were oxidized by a large excess of terzbutyl hydroperoxide and one equivalent of sodium hydroxide, without any transition metal catalyst. Aliphatic primary alcohols, however, were converted into esters under these conditions, by Tishenko reaction of the intermediate aldehyde. One convenient way to prepare malonic acid on a large scale is dehydrogenation of 1,3-propanediol or 3-hydroxypropanol. The latter can be readily obtained from acrolein and water. Here, the oxidation was achieved with oxygen and a large amount of supported palladium under almost neutral conditions. Benzylic alcohols are easy to oxidize. Here, picolinic acid was prepared from the alcohol by oxidation with air. The reaction was catalyzed by a silver-carbene complex and a large excess of potassium hydroxide. Nitric acid, another convenient oxidant, is easier to handle than air or pure oxygen. In this example, a primary aliphatic alcohol was oxidized with an excess of nitric acid and catalytic quantities of nitrite and acetic acid. Nitrite was required to shorten the induction period by formation of NO2, a stable radical and key intermediate in these oxidations. Unlike most previous examples, here the reaction conditions were strongly acidic. Small-scale or high-temperature gas-phase oxidations with nitric acid do not require any catalysts. In this example, isoamyl alcohol was oxidized simply by stirring with a 5-fold excess of concentrated nitric acid at 30 degrees Celsius. Care should, however, always be taken with these reactions because of their exothermicity and unpredictable induction periods. Here, dihydropyrane was first hydrolyzed and then oxidized to glutaric acid with nitric acid. A good yield of diacid was obtained, without the need of any organic solvent or transition metals. Nitric acid combined with catalytic vanadate can even cause CC-bond cleavage, as in this example. Here, cyclohexanol was oxidized to adipic acid, and the reaction already proceeded at 60 degrees Celsius and was complete after only 1 hour. Instead of alcohols, esters can also be suitable starting materials for these oxidations, as shown here. Despite the acidic reaction conditions, no displacement of fluoride occurred. Another convenient oxidant is hypochlorite. In this example, heptanol was oxidized to heptanoic acid by treatment with an excess of bleach and catalytic amounts of nickel chloride. One disadvantage of hypochlorite is its ability to chlorinate arenes, alkenes, enolates, and other nucleophiles. Also, chloride in combination with TEMPO can be used to convert primary alcohols into carboxylic acids. Electrophilic chlorination does not proceed here as readily as with hypochlorite. No chlorination of the arene occurred in this example, and a quantitative yield of aryl acetic acid resulted. With alkenes or more electron-rich arenes, however, larger amounts of chlorinated byproducts were obtained under these conditions. The neutral, mild reaction conditions of oxidations with chloride can enable highly selective oxidations, as in this case. Here, a diol was oxidized in high yield to an alpha-hydroxy acid. No saponification of the benzoate or oxidation of the secondary alcohol occurred. Another electrophilic chlorinating reagent suitable for the oxidation of primary alcohols is trichloroisocyanuric acid. In this example, the oxidation was catalyzed by 1% of ruthenium chloride and was conducted under slightly alkaline conditions. With NBS, even enantioselective oxidations have been reported. Here, a diol was oxidized only once to a methyl ester with NBS and 10% of an enantiomerically pure copper complex. Also, amine oxides can be used as oxidants, but these reagents are less convenient than hydrogen peroxide or nitric acid. The catalyst in this example was perruthenate, and the oxidation was conducted without any protic solvent. Under the same conditions, also structurally more complex alcohols could be oxidized, as in the second equation on this slide. No racemization of the products occurred. Also, permanganate can bring about the oxidation of primary alcohols. Here, a small amount of a degradation byproduct was formed, probably by alpha-hydroxylation of the main product and further oxidation and decarbonylation. Like amine oxides, permanganate is not very convenient because of the large amount of non-combustible waste. In this example, a phase transfer catalyst was required. Unfortunately, tetrabutylammonium salts were oxidized to butanoic acid, which was difficult to separate from the desired product. This problem could be solved by using tetraethylammonium bisulfate as catalyst instead of the common tetrabutylammonium salts. Let's check some potential side reactions. As you have seen, some of the reaction conditions described above are rather harsh and can cause the oxidation of other functional groups. Particularly sensitive are ketones, aldehydes, amines, thiols, thioethers, benzyl halides, quaternary ammonium salts, and even alkenes, alkanes, and arenes. In the next videos, we'll have a look at the oxidation to carboxylic acids of some of these groups. Oxidations with oxygen can always lead to the formation of potentially explosive hydroperoxides. Most volatile organic compounds will also form explosive mixtures with oxygen, and air or oxygen are therefore not really convenient oxidants. Such reactions require a very thorough safety assessment and optimization to be run safely, if this is possible at all. Some of the oxidants described above can also bring about oxidative halogenations, nitrations, or nitrosations. An excess of these reagents should thus be avoided. If the reaction conditions are strongly alkaline or acidic, aldehydes or ketones formed as intermediates may undergo condensation reactions. This can sometimes be prevented by lowering the concentration. Another typical byproduct are esters formed by Tichenko reaction of intermediate aldehydes, as in this example. Strong bases or acids or a longer reaction time should cause saponification and complete oxidation of these esters. Here's a selection of some more examples, which you can also find in the description of this video. Subscribers can find the PDF version of this presentation under the Community tab. The next video of this playlist is about the oxidation of alkanes, for instance alkyl arenes and cycloalkanes. These reactions are rarely applicable to advanced multifunctional intermediates, but give access to certain types of carboxylic acid. So don't miss it.